All right, hello pre-cal. Focus this as well. All right, not pre-cal. This is calculus. Oh Lord. Okay, this is lesson 1.5 algebraic limits. So we have been talking about all the different ways that we can find limits of functions. So whether that's by looking at the graph, or maybe we do a numeric limit where we can use a table and get x values that are very, very close to what we're looking for. But it's important to remember that when we are evaluating a limit, we need to look from the left side of the value and the right side of the value. Today for work, we have two little worksheets. They're really quite good, but let me know if you want more practice because, this is definitely one of the areas where more practice is a good thing. So I could send also another like a picture or a PDF of the book, and there's lots of practice problems that you could do. These are Kuta worksheets. Please check your answers and know that on the critical thinking ones, yes, try it, give it a shot. But definitely, if you need to use the answers to, help you answer it if you need to. You definitely should take time to think about those critical thinking questions because the questions on the AP test are very involved. So it is important to try and stretch your thinking. Algebraic limits, we want to be able to figure out a strategy. So the first thing that's always easiest is direct substitution, but does that work all the time? No, but it's certainly the first stop along the way. So can you do direct substitution? Maybe, give it a try. So how do you know when you can't? All right, so if you get like 0 over 0, this is an indeterminate form. Or if you get something over 0, so again, if you get something that's undefined, something that doesn't work, then you have to figure out another strategy, which could be maybe factoring. So that would be the dividing out technique. So factoring and reducing. Maybe you need to rationalize. And hopefully you'll start to see what those kind of look like. Eventually we might do some trig substitution. So maybe there's some trig substitutions we can do. We won't talk about that right now, but hopefully soon. And then another one, it might be that we really just need to do some algebra to simplify. Like thinking like common denominators. So, we have all these algebraic strategies that we could use if we need to. If we get some kind of indeterminate form that's undefined or this indeterminate form. We'll learn more about this form in future chapters. So let's see. Again, pause the video if you need to. We're going to do a tiny bit of going back to review. We want to discuss the continuity. What does continuity mean? It means the limit as x approaches some value of our function is equal to the function at that value. So the function has to actually have that same limit value. And so when we look at this is kind of an interesting thing. Here you can see our function equals 5 only when x is equal to 3. So that's sort of an ordered pair. When x is 3, our output value is 5. And then here, this is a function that looks like a rational function. We can see that it's undefined at 3. And that's when we're not allowed to equal it anyway. So kind of interesting. What we need to look at then is we need to look at the limit, first of all, we have to look at the limit of our function. And that limit has to exist. So in order for that limit to exist, the limit has to work from the left and the right. Well, let's see what happens here. The limit as x approaches 3, you'll notice this is undefined at 3, from the left of this piece of our function. And I'm going to go ahead, and it looks like this double bubbles. So x minus 3 times x plus 1, there we go, over x minus 3. Okay, well, we can see that that's going to reduce. That's nice, that's convenient. Of x plus 1. And now I couldn't plug in directly before because it would have been undefined. But now that we've simplified our function, now I actually can plug in. And this limit, as we get really close to 3 from the left-hand side, we get to plug that in and we get 4. And let's see, what is the limit as x approaches 3 from the right-hand side? Well, same thing. We're using the same function because this function works a whole lot. And there's only this one point where this function doesn't have that value. So from the right, we're still on this function, which means that same thing, it'll reduce to this. And again, we can now plug in. So again, it looks like the limit as x approaches 3 of our function equals 4 because they both agree. But let's look at our function evaluated at 3. F evaluated at 3, well, the only place where we're allowed to equal 3 is right here, which is 5. So we know that the limit as x approaches 3 of our function equals 4. And the limit, which does not equal I don't know the best way to say this. And I'll just write it out. And f of 3 equals 5, which means the function is not continuous at x equals 3. And that was really the only place we had to worry about. And we could see that right here where we knew the denominator was undefined at 3. Everywhere else, we have a nice shape here. And so what does this look like? Ultimately, it's going to look like the line x plus 1, but it has a hole at 3 when x is 3. And it has this value. When x is 3, it has the value 5. So this hole is at 3, 4, and it has the defined point at 5. So that's what that looks like. And we can see that that removable discontinuity at x equals 3. All right, so again, here we have another example of find this value of a so that g of x is a continuous function. Well, we did one like this in the previous lesson. So to be continuous, the big thing is that our limits from the left and the right have to agree. And also, our function has to have that same output value as well. So we're going to start with the limits. It looks like change is happening at 2 here. So we want our limit from the left of g of x to equal our limit from the right of g of x. And that's where we're going to start. So remember, when we look at these piecewise functions, for x values greater than 2, well, for x values greater than 2, that would be to the right of 2. And x values littler than 2 would be to the left of 2. So we're using this function when we're looking at the limit from the left. And again, we can plug that in. And that's going to be 2 minus 3 is negative 1. sorry. Oh, we'll plug it in just a second. And then here from the right side, we're going to use this top equation. That's what happens. That's what we use when we're slightly to the right here. 3x squared plus a. All right, now these are supposed to be equal when x is 2. So we're going to go ahead and plug that in. So 2 minus 3 equals 3 times 2 squared plus a. And that's negative 1. Here, 4 times 3 is 12 plus a. And we get a equals negative 13. So that is the value of a that should produce a continuous function. So maybe we want to double check. We're going to go ahead and plug in that value. So that's 3x squared minus 13 when x is greater than 2, and x minus 3 when x is less than or equal to 2. And we want to double check. We want to make sure that g of 2, well, basically equals negative 1 is what it should turn out to be. So at 2, we get to plug it in. We're equal to 2 here, and that's going to be 2 minus 3, which is negative 1. All right. So our limits now will work as well. It also works on this side when we know that a is negative 13. So 12 minus 13 gives us that negative 1 as well. So now everything is negative 1, which is what we want. All right. So we have learned about the properties of limits in the previous lesson, and that's what we want to do here. Use those properties and use proper notation. So here to evaluate this, I'm going to model proper notation, and you need to know how to do this. And but in a multiple choice test, they won't be grading your work, so that's kind of convenient. But here we go. First of all, I have the sum of 2 functions, so that means that I can take the limit of each portion. All right, and then this is the scalar multiple times some well-behaved function. So that turns out we can just do 4 times the limit as x approaches 2 of x squared. The limit of a constant function is the constant function. And here, the limit of a nice little well-behaved polynomial, we can just do a nice direct substitution. That's going to be 4 times 2 squared. So 16 plus 3 is 19. And that's showing proper notation. Here we have the quotient property. So the quotient property says that I can take the limit of the numerator over the limit of the denominator. All right, now within that, I can get highly technical here, and I don't really always do this, understand, okay? So, but this would be the technical way to do things. Do I think you need to do it all the time? No, no, I don't. I'm going to be very, very honest. Here we have a sum of functions, so really that would be the limit as x approaches 1 of x squared, plus the limit as x approaches 1 of x, plus the limit as x approaches 1 of 2. Again, we have a sum of functions, so it is the limit of each function, the limit of x, and the limit as x approaches 1 of a constant function. So again, it seems like a lot of nasty work. Yes, it's true. Now we can do our substitution. So we'd have 1 squared plus 1. This is a constant function, so it's always just that value of 2. And same thing down here, plugging in the 1 and that constant function, unchanging. All right. 1 plus 1 plus 2 is 4. over 2, which is 2. So yes, this is, I would say, ridiculous. I think this is probably a good step, and then maybe you can be like, all right, I can just direct substitution everything and get to here. I think that's okay. So, this is good. For showing work for me, I can't imagine you would have to do anything more than that. Okay, so what if you can't just plug in directly? So you can see here, if I were to try to plug in, I would get undefined. All right, so I can't just plug in. And because I can't plug in, I need to do some algebra. So we're going to have a factoring technique is possible. And again, we've been talking about this. So we are going to do some simplifying. So this is going to be equal to the limit as x approaches 1. This is difference of cubes. Small bubble, big bubble, minus, plus, plus. X cubed is x cubed, and 1 cubed is 1. Square the first thing, multiply in the middle, square the last, remember that? Over x minus 1. All right, now these reduce, which is very handy, and we can rewrite our limit of x squared plus x plus 1. And now direct substitution is just fine. I could write it out, the limit as x approaches 1 of x squared plus the limit as x approaches 1 of x plus the limit of 1. But I'm just going to go ahead and do 1 squared plus 1 is 3. So this limit is 3. Follow up. What about this limit? That's interesting. What's the one difference here? So I'm going to try the same idea. Small bubble, big bubble here for the numerator. X plus 1 plus minus plus. You'll notice that this one does not reduce. These signs are different. And I actually can't find this limit. There's nothing algebraically that I can do to this to help clean it up. You can also see it graphically if you were to graph this one. So x cubed plus 1 over x minus 1. It's always a good idea. I love using my calculator to justify what I'm thinking here. You can see that at 1, we have a vertical asymptote just sort of peeking out. I'm gonna change my window. Maybe go up to 20. See a little better. Yeah, there's just a little bit up there. I went the wrong direction, that's why. Funny. All right, oh Lord. Here we go. That's what I meant to do. All right, and there's the rest of that little weird graph. So you can see there's this vertical asymptote that's happening at 1. And that's because there's a vertical asymptote. The limit does not exist. And so that is pretty important. Okay, this is also an interesting one. You'll notice that this function, if I were to just plug in a 2, it would be undefined. But this is very specific. It's actually talking about plugging in a number slightly larger than 2. And so we could, maybe plug in a number slightly larger than 2 and see what we get. Well, what's going to happen if we have a number slightly larger than 2? Interesting. Well, let's think about that. What if we tried that? What if we tried a number slightly larger than 2? So this sort of goes to the question of maybe looking at the table and seeing values that are, getting closer and closer and closer to 2 on the right side. So we could do that. We could plug in values like, I don't know, 2.0001 over 2.0001 minus 2. Interesting. Well, let's see what happens. I'm just playing around here. 0.1 divided by 2.0001 minus 2. Wow, we get 20,001? Say what? Okay, let's talk about that, because this is kind of an interesting thing. When we subtract 2, we have a very, very, very small fraction here in the denominator, and this is really important. This fraction is a fraction, and I'm going to rewrite that, in fact. It is the fraction 1 over 1, 2, 3, 4 zeros. Let's see, 1 over, let me double check. I think that's right. 5 zeros. There we go. 1 over 1, 2, 3, 4. Oh, I'm in scientific notation again? All right. Oh, 4. I did 5. Oh, okay. Great. 1, 2, 3, 4. Yes. Okay. So this is that fraction. Well, we're taking a number. We don't like to divide by fractions, right? And so we would take our 2.0001 and multiply by the fraction 10,000 over 1. So what happens when we're dividing by something very small? Our number becomes very, very large. And so you can imagine that if I added another 0 in here, then this becomes 200,000. And if I added another 0 to 2 million, all right? And so what's happening here? This function is going to infinity. Well, let's look at the graph and also look at it that way. So x over x minus 2. All right, so here we are at x equals 2. You see we have a vertical asymptote. And so this is a great thing that you can do. You can plug in values that are slightly larger and see what happens. We get this huge number. And if we use even numbers closer and closer to 2, it's going to get even huger, if that were a word. You can see as we get closer and closer to 2 on the x-axis, our function is growing all the way up to infinity. So this limit does not exist. But if you had the option to say it grows to infinity, that's okay. But remember, limits have to be numbers. That's why it doesn't exist. So kind of interesting. You can use numeric values sometimes too. All right, here you see some interesting stuff here. You'll notice that if you were to try to just plug in directly, we would get something undefined again. So because it's undefined, we have to use an algebra technique. This one we're going to rationalize. All right, so we can rationalize. So what I'm going to do is I am going to, wherever that radical is, I am going to rationalize, multiply by the conjugate, which is I'm going to multiply top and bottom by x plus 2, radical x plus 2, sorry, top and bottom. Now I'm allowed to do that? Yes, because I am simply multiplying by an equivalent to 1. Now, we can go ahead and multiply the numerator together. Radical x times radical x is x. The outside is positive 2 radical x. The inside is negative 2 radical x. And last times last is negative 4. Oh, what happened? Oh, these middle terms cancel out. Isn't that handy? And in the denominator, we're left with x minus 4 times radical x plus 2. You'll notice they didn't multiply those together. Why? Because in my next step, I'm left with x minus 4 in the numerator x minus 4 in the denominator. How about that? And so you can see those reduce to a 1. And my limit is getting better now. Now I actually can go ahead and do that direct substitution. So that is the rationalizing technique. And we would get 1 over radical 4 plus 2. Square root of 4 is 2, which gives me a limit of 1/4. We can do the same thing over here. Again, if I tried direct substitution, it is undefined. We can't do that. And so once again, I'm going to rationalize. And all I have to do is multiply by the conjugate. X plus 1 plus 1, top and bottom. You'll notice I just changed the 1 sign. Don't change more than that. All right, I'm going to pause the video and complete the rest of this exercise. You should pause it and test it out too. All right, so we get 1/2 for the limit as x approaches 0. I do want to point out these middle terms, the outer and the inner product, are always going to cancel, so you don't have to write them out. Certainly it's easier that way, but you know, I'm modeling for notes, so know that you don't have to write them out. Here we just get x in the top because we have x plus 1 minus 1, so the ones cancel out. Or they add out. Cancel is the wrong word. And from there, we notice that now we're able to plug in directly. All right. Almost done. So here's an example. Again, if we tried to plug in, it would be undefined. And that, again, causes an issue. But what can we do? Well, here, common denominators. We have a complex fraction, so we can try and simplify this complex denominator. And I'm running out of time. So it looks like this last one, there's no x in here. I think we can probably just do direct substitution on this. So keep that in mind. We're going to go ahead and get a common denominator for this numerator. So I'm going to multiply top and bottom by 3. And on this side, I'm going to multiply top and bottom by x plus 3. Go ahead and pause your video and see if you can simplify that fraction. All right, so I finished working out that example. The first numerator here is just 3. This is the part you're going to miss, distributing your negative. This is -1 times x plus 3, which is going to give you negative x minus 3. Be careful. Again, the 3 and -3 add to be 0, and we're left with a negative x on top. Watch your negatives. Fraction divided by fraction, keep, change, flip. So we're multiplying by the reciprocal, and the x's reduce, and then we're able to plug in directly. And last here, again, I'm just going to try doing a little direct substitution. That'd be sine of 2 pi over 12. Well, that's just sine of pi over 6. And thinking about your unit circle, pi over 6 is right here. That has a sine value of 1/2. Easy peasy. That one we could do direct substitution. So you have a couple methods, whether it's factoring or rationalizing, or maybe simplifying complex fractions that you can use to help evaluate limits. All right, ladies and gentlemen, make sure you check your answers on those worksheets. Have a great day.